Welcome to Lab 5, Choose Your Own Adventure. For this lab, I got to choose to investigate and model any system that interested me. I chose to throw a ball up and model the effects of drag and gravity, as well as the effects on the kinetic and potential energy, as well as the total energy. The result was that the total energy changed because of the effects of drag. The first set of physics principles has to do with Newton's second law, which is that the acceleration of an object is dependent upon two variables, the net force acting upon the object and the mass of the object. For these equations, we use Vf equals Vi plus F net over m times delta t. We use Rf equals Ri plus Vf times delta t. We use F net equals force of gravity plus the drag force. And we know the force of gravity is negative mg times j hat, and the force of drag is negative b v squared times negative j hat. The energies are quite simple. We know kinetic energy equals 1/2 mv squared, we know potential energy equals mgh, and we know the total energy is equal to kinetic energy plus the potential energy. Here's my tracker software where I analyze the motion of the ball. Some important info from the tracker software is that it took a total of 1.033 seconds in order for the ball to fall. Also, the starting position was 0, negative 1.560, and the initial velocity from going up was 0, and then 0.642 minus negative 0.156 over 0.4, which is just 0, 1.9950. And this initial velocity is important because the ball goes up before it goes down. The first part of the code is simple. It's just from Lab 2 and Lab 4. The first 18 lines is simply the graph of the position versus time for the ball, and lines 21 through 30 is just the graph of the change in energy. Line 36 is simply the mass of the lacrosse ball, and 40 and 41 is the starting position and velocity. The delta t is 0.005, which is used in Lab 2 and in Lab 4. The second part of the code is much more complicated. We know that g is equal to 9.8, and the j hat vector is in the y direction. We know that b is equal to 0.22 by running the code many times until the values were close to the ones in the tracker software. K and u are simply 1/2 mv squared and negative mgh. We also know that the time is less than 1.033 since that's the time that it took for the ball to fall, and we know that the force of gravity is equal to mg j hat, or negative mg j hat, and the force of drag is equal to negative b times the magnitude of the ball's velocity squared times negative j hat. And we know the net force is the force of gravity plus the force of drag. Then we solve for the velocity and position, which is simply Newton's second law, which is in the physics principles. We then updated the kinetic, potential, and total energy and solved for the delta K, U, and E of each to plot it on the graph. This is what happens when you run the code. One of the biggest things you might notice was that the energy was not conserved. That means in the graph, the delta E was not equal to 0. This is because drag isn't accounted for in energy because we can't account for rotational kinetic energy, only translational, and also we can't account for heat. Therefore, even though energy might be conserved, we cannot model this because we do not have the proper equations or instruments to do it. Now let's look at the similarities of the model and the tracker software. First, looking at the graph. Looking at the graph in the code, we see that it goes up and then it goes down consistently. Similarly, in the tracker software, it does the same exact thing in the y direction. In this, the x direction doesn't matter. Now looking at the times, we see that the final time is 1.035 and the final time is 1.033, and the number is negative 1.24 for the y and negative 1.205 for the y in the tracker software. Therefore, my model did a very, very good job in predicting the motion of a ball, similarly to what I got in tracker software. In conclusion, this lab was not very difficult. It simply used parts from Lab 2 and Lab 4, as well as a different type of video throwing the ball up in the air instead of just dropping it down. However, our model was very accurate to the data in tracker. Going back to the similarity part, they are almost identical when it comes to the numbers and the graphs. However, the energy was not conserved, which was probably because we couldn't model the energy from drag, which caused an error. Therefore, to fix this, we would have to research how to solve for energy of drag force in order to make sure that the energy was conserved in the end. However, we learned today that the different physics systems can go together and be modeled together, And just because we did one lab one week and one lab the other week doesn't mean they're not similar.